Yeah, so short who am I? I did my master thesis in the TU Berlin about this topic, and the paper resulted from that. Currently, I'm working as a security consultant and researcher in Berlin, Germany, and my co-author Florian was also my supervisor for the thesis, and he's leading the chair for distributed security infrastructure there. So our goals were that we were looking into client-side request forgery in the QUIC protocol, and we were able to derive 3 unique attack modalities. And with the different attack modalities, we showed 2 different attacks that were possible with them. So short QUIC background, I think most of you know it by now. So we have QUIC as combining the TCP transport layer protocol capabilities with the TLS encryption capabilities into one protocol, as well as some multi-streaming capabilities. And this allows for much faster connection setup as we have this combined handshake. On the other hand, QUIC is built on top of UDP to make it compatible with the current network stacks, but this has the implication that we're technically having a user-land protocol here, and it's not longer living in the kernel, the transport layer. One unique feature that arises through this is that we have connection migration, so a client can change its source IP address and port, and the connection can still be maintained, for example, by so the server detects this migration, and then it sends a path challenge containing a token. The client then takes this token and reflects it, and after that, the connection can be maintained. So request forgery, in our case, we talk about client-side request forgery, so that means the attacker here is always the client, and we talk to a QUIC server, in our case called the victim, and our goal is that we trick this victim into sending packets to a target. And we do that for 2 primary reasons. Either we want to leverage the position in the network to address internal targets, for example, or we want to utilize the resources of the victim, for example, the bandwidth to DOS attacks. So the first technique that we looked at was a connection migration request forgery. This is where we use this connection migration feature. So the attacker first established a full connection, and at some point we spoof the source IP address or port, and then the victim, as it's not able to tell if this is a valid migration or a spoofed one, sends this path challenge to the target. The second technique directly uses the server initial messages we have. So directly on contacting the server, I spoof the source IP address, and then the victim thinks, oh, this is a new connection attempt from the target IP, and I will send my full server initial packet to this target. And the last one is a variation of this. So QUIC supports version negotiation. In this case, we can spoof also the version number to a number that is not known. And then the victim thinks, oh, I don't know this, I will send the version negotiation, which is indicated that the version fields are all set to 0, and the packets contain then all the supported version numbers. So, talking about what we can do with that, first we looked at protocol impersonation. So the goal was here that we trick the target into thinking it's receiving another protocol. And therefore we looked into the controllable byte space we have, so we were looking at the headers of QUIC. And here we were focusing only on the unencrypted parts. There might be some cryptographic attacks as well, but in this scope we only looked at the unencrypted header fields. So for the connection migration, we have a short header format where we have 1 byte that has control flags, followed by up to 20 bytes of the CID. This is the green part here. So the CID is the primary connection identifier that is used in QUIC to identify the connections. And this is followed by 4 bytes for the length of the packet, and these are partially controllable as we can let the numbers ramp up if we keep the connection open longer. For the 2 other cases, we have a long header format. This has also 1 byte of control flags, but then we have 4 bytes of the version number, which then is followed by 1 length byte that indicates the length of the CID. So the CID can be 0 to up to 20 bytes in the current standard, and so this byte is partially controllable, but only in this range that is allowed. For this case, we have a special case, as we have like a special edition there. If the server reflects the proposed CID by the client, we can double basically the amount of space, but this has not to be done. And then we have a really interesting case, which is the last one with the version negotiation to support future changes in the protocol. The server has to allow up to the full byte range that is encodable in this 1 byte. So we can have per CID up to 255 bytes. And additionally, the server has to reflect both CIDs, so we result in 512 bytes that are controllable. And this is sufficient to impersonate some protocols, as we will show in the later slides. So we made here a proof of concept to impersonate a DNS request. Here we have the beginning of the packet with the 2 comparisons and the interpretations. And we see that the flags and the version that is in the long header of QUIC correlates to the ID, which can be very arbitrary in QUIC, in DNS. And then we have the flags, which here are all 0. This is OK for a DNS request, as this is still a valid query. Then we have the DC ID length, which we set to 7, not because we want to send 7 requests, but because we want to skip over some parts we don't want to set. And then in the second SCID here, we can set our payload, in this case the host name. And if someone of you is familiar with ASCII, we have 74752D, which results in TU minus, and then of course Berlin. Looking at this in Wireshark in a capture, let me enlarge this on the left. Here we have the QUIC interpretation. So we see there is an initial message where we spoof the source, the IP address of the Google DNS server, 8888, and then we also have a wrong version in there, and therefore the server sends this version negotiation packet to the DNS server. Of course, the message that comes back from the DNS server does not make any sense in the QUIC context here. But if we change to interpreting this bytes, the byte stream as DNS, we see, okay, this first message is interpreted as a valid standard query to TU Berlin, and then we see that we indeed get back a standard query response from the Google DNS server, giving us the IP addresses for TU Berlin. Yeah, so what can we do about that? First thing would to not reflect the second CID. So this could be done immediately without too much changes. Another option would be that we deploy hashing. So the server could send a seed, instead of the CID, and then the server uses the hash of that. In this case, the server or the attacker would require to calculate the inverse of the hash, which should be infeasible. This has some issues with routing, as we have 2 different values here. Another option then would be masking, where we add another field to the QUIC header, and the server then uses this randomly generated value in this field, or it generates it randomly, and then masks the rest of the header so it appears random and cannot be forged for payloads. Yeah, so the second attack we were looking at is traffic amplification. So here we want that basically the victim sends more traffic to the target than we have to send as an attacker. And we focus here primarily on the path amplification. So this means the difference between what is sent to the target and what we have to send on the new path with the spoofed IP address. We do this because there is a path amplification limit in QUIC specified that says, okay, it's only allowed to send 3 times the amount of data received on any unvalidated path. And therefore, we were looking into, okay, where are pitfalls, where can this go wrong? And therefore, we identified 3 major pitfalls where it could go wrong. So we have the minimum path requirements. So QUIC also has to ensure that the path supports packets up to 1,200 byte length. And this is ensured that the initial packets are padded. But of course, in the connection migration case, if I only receive a really small acknowledgement, then sending like this padded packet will directly violate this limit. Second problem is if the server initial packet is much larger because it contains all the certificate information for TLS, this could also violate the issue, violate the limit. The third is basically worsening the first 2. So we have the reliability here. During the connection migration, we don't have the normal reliability mechanisms, so servers can send multiple of these path challenges, either in a burst or with resends. And of course, if we already have an issue with one path challenge, sending multiple ones will definitely surpass this limit. And similar case with the server initial packet. There, if the server does not receive an acknowledgement, usually it would resend a packet. But of course, here, if we already, again, have an issue with one of the server initial packets, resending it will also violate that. And what can we do here? yeah, so unfortunately or fortunately, we have everything in the specification here. But as we will show in the evaluation, this can go wrong, and it does go wrong. So yeah, what did we do for our evaluation? So we looked at 13 open source implementations of QUIC that were available at the time. And we had our client set up with one of the QUIC clients, intercepting the packets and then changing the parts that are required for our attacks. And on the other hand, we ran the servers in a Dockerized setup, intercepting the traffic with Wireshark to see what's happening. And if we look at what all the parameters we analyzed, I can't go into much detail in the time here, but if you look at the pattern, you see, okay, there is a discrepancy between all the different implementations, and there is a discrepancy between the implementations and the specifications. So all of them handle different things differently. And this means that also we might have some issues with these pitfalls. And if you look into the columns where we have a path amplification factor of larger than 3, we see, okay, we do have these cases here. And looking at this in numbers, we see that we have 5 of the implementations that do exert really significant path amplification vectors for different scenarios. And most of them rely on these pitfalls that we uncovered earlier. We disclosed this to all the developers, and it should be fixed in most of the implementations, or it can be turned off by now. Yeah, so in conclusion, what did we show? So we showed that all the 13 implementations were indeed vulnerable to one of the techniques. So this means that, or this results because we have these issues that allow us to use these techniques really in the protocol specification itself, not as a bug. And even though that we have considerations about it with amplification protection that is covered in the specification, we have these really unique edge cases where it can go wrong, and sometimes if developers look more into more performance, they will have issues adhering to the bandwidth amplification limit. Of course, these vendors were notified as mentioned. And yeah, the second attack that we have with protocol impersonation that is possible with only VNRF, here we don't have currently a built-in solution or built-in mechanism to avoid that. Of course, there could be something done on the network level, so we could deploy port filters or IP filters, but these might not be feasible in all situations, in all scenarios. So currently, the best way, in our opinion, is that we propose some changes to the specification to cover this in all the cases. Yeah, and with this, pretty much close to the end of my talk, we also published a blog post if you're a bit more interested into the technical side and also want to see a short demo that you can find here. And of course, you can always find the details in the paper. And yeah, thanks for listening. And yeah, I'm now ready for questions.
So you talk about these amplification attacks. And basically highlight that like these are all specified what you're supposed to do, but there's tension with different reliability pieces of that. At the same time, you've got a whole bunch of people that clearly fail to do them. Do you have any suggestions for how to make this less error-prone or more clearly? Yeah.
So of course that's always the discussion. If we want, you could do some edge cases in all the cases, so that we basically say okay, we do always 2 path validations instead of one, first validating the path and then validating the path requirements precise. Of course, there's always a discussion if we now have an issue with the performance. So I think at this point the best part would be maybe restructure or like emphasize it in the specification of the points where it's relevant. Yeah.
Sounds good. Any other questions? Here we go.
Hi, I'm Jared Chandler from Tufts. I was curious about how you determined that you could embed DNS inside the manipulatable part of QUIC. Is that a manual process? And do you have any thoughts about maybe how that could be automated? So if you had some set of protocols, you could determine automatically what you could actually stick inside there.
Yeah, so for this was a manual process, as it requires some moving around the bytes at this point. I think, of course, you have some limitations with the IDs and the bytes that are not controllable. So I think it would be hard to find an automated way for all the different variations of the protocol. So I think it will not be possible to impersonate every message of protocol, but multiple. So this is like a creative process here, and I think it will be hard to find an automated way.
Other questions? Okay, one more then. So QUIC is really one of our first attempts in a while to actually design one of these protocols from scratch again. Doing this analysis and seeing where there are vulnerabilities, do you have recommendations for the next time we attempt to build a protocol from scratch? Where there are improvements to make?
Well, that's a hard question, I would say. So designing from scratch is always hard. I think it was really a good idea to utilize TLS as we currently have it without redefining everything there and creating everything new. So yeah, I think at the end, there isn't like this one guideline I could suggest you.
Fair enough. Thank you so much.